and we'll get going. All right. So as I don't know if Brad mentioned last week, or for those of you that heard me earlier, so Brad is on vacation this week, so I'll be covering lectures, and we're really just going to spend some time going over factors in multiple linear regression and looking at that, because so far we've really just been talking about continuous predictor variables and continuous response variables. So we'll get into that. My goal at this point, we'll see how we get through the material today and Wednesday. But if we're feeling comfortable enough, my goal is to cancel our lecture on Friday to give you guys that extra hour to, wrap up your assignment 7 that's due before the break. And just to a reminder, we won't post a new assignment to be worked on over the break, because our assignment 9 will actually be a combination of what we're learning this week with factors, as well as model selection that we'll be covering the week we get back from the break. So again, you won't have the only homework assignment that you would have to work on for this course would be assignment 8 that was posted a week and a half ago. That's the, as Brad calls it, the what do I want to be when I grow up assignment. So, you guys can be working on that over the break if you'd like to, but you also have additional time when you get back to wrap that up. So, again, I know in talking to some of you all that you have a lot of, to-dos like homework assignments and everything as we go into the holidays, and we don't want to add that extra pressure on you, because I recognize you all need a break and so do we. So so yeah, we'll give you guys as much of a break as we can over Thanksgiving, but if you want to do some work on assignment 8, you're welcome to do that too. All right. Okay, so let me share my screen real quick and we will get started. I'm actually going to move some screens here real quick. And okay, let me pull up my chat too, so I don't miss anything there. All right. So I did add this MLR dash factors RMD to eCampus. So, you can download that. I will likely, I can guarantee you I'm going to make some edits to it as we go through things today. So I will re-upload the revised version at the end of class today as we work through an example, so that way you have the latest and greatest to reference on eCampus. One thing I will note is that when you go to knit the file as it stands right now, you're probably going to get an error. And that's because we are going to work with an external data set for an example that you'll probably need to change. Well, you'll definitely need to change the path to that file in your code. So right now it is on line, let's see, it's down here at the bottom. So line 155, you'll probably have to change before you're able to knit the file as it stands now. So you'll need to put in the path to wherever you save the CSV, and the CSV we've worked with previously on a homework assignment. So it's, something you may already have saved locally if you don't go clean up your files frequently. So it might be in your download folder already, but I added that CSV also to the eCampus module content for quicker reference if you need it, if you need to re-download it. Okay. All right. So I have gone ahead though, because it knows where my working directory is. I was able to successfully knit the file. So I'm going to go ahead and scroll up here to the top, and we're going to talk through a few things before we look at examples. Okay. So like I introduced the course, so far we have used continuous variables in our predictor variables and our response variables. So what that means is, we're working with either integer or numeric values or continuous values. So they're all numeric in type. They're not factors. So we use the word factors, but we're going to use it interchangeably also with categorical variables, which really is what they're referred to. But you'll see in RStudio or in R, it'll tell you when it starts to tell you your data types, it'll call it factor with however many levels. So a lot of times there'll be 2 levels. So it's a binary categorical variable. So true, false, yes, no, 0, 1, things like that are going to be our binary variables. And then, but they can also take on a number of options. So another one that we may have is, let's see, political affiliation. So Democrat, Republican, moderate. So you'd have 3 levels, a factor with 3 levels in that sort of a variable. Okay, so again, it can take on a number of different options. The other thing too is, and I think I have an example, if not for today's class, for Wednesdays, where sometimes when you read in your data set, it may not recognize that particular variable as a factor right away. It might just view it as a character, especially if it has several levels to it, more than 2 levels. It may read it as a character value. So there are tricks to being able to force R to viewing it as a factor. So again, I'll make sure we have an example of that, if not today, on Wednesday, so that you can see what that would look like. And some of you guys have actually even asked about that when doing some of our data visualization work previously, in wanting to do some color, adding color as a third view. So that'll be a refresher for some of you all and something new for others. Okay. So, today we're going to be looking at specifically using categorical variables as our predictors. Okay. So not as the response variables. We're going to cover that on Wednesday. But today we're looking at them from a predictor standpoint. So let's talk about the math behind this for just a little bit. So, basically what we're going to do, we're going to discuss a definition of a new term. So this is an indicator here. So indicator of X equals A. So let's just say right now we have a binary variable of yes and no. Okay, so X equals A, we're going to say A is our yes. And so this is the indicator when that variable takes on value A, or in our example, yes. So when we see I of X equals A, it is either a 1 if X is equal to A, or yes, or it's 0 otherwise. Okay, so it's either that or it's something else. So even if we had multiple different levels to a factor, it's just checking for that particular case. So in the example I gave earlier of Democrat, Republican, moderate, so X equals Democrat. If our X observation, if X equals moderate or Democrat, I think I just said X equals Republican. So if it's one of the other two, then basically it'd be given a 0. And if it's what we define for A, then it's given a 1. Okay. So using factors as a predictor variable in regression allows us to model subpopulations of data differently. For example, if we believe that men and women have a different relationship in height and weight, they could have different intercepts or slopes, which we can model directly. And we'll talk about that in just a bit. The use of factors allow us flexibility in modeling. The question is, how do they play into creating models? So let's say for our purposes that we have a continuous response variable Y and a categorical predictor variable F that has 3 levels, A, B, and C. This type of model is known as a one-way design or a one-factor design. Okay, so we're just looking at one factor and its impact on one continuous response variable Y. So it's our belief that the 3 levels should result in different models. The question could also be, are the 3 groups different? There are 2 different ways to model this type of data. So the first one is gives us a baseline for comparison. And frankly, this is the method that we're going to apply. So when we give you a homework assignment, this is the method we're going to be looking for you to apply. You could do the other one, but quite frankly, this the baseline is a little bit more related to how we've taught you to interpret models thus far using continuous predictor variables. Okay, so we have the expected value of y given f is equal to beta naught. Okay, so this looks like what we typically have seen, plus beta b, the indicator, so I of f equals b, plus beta c, indicator of I of f equals c. So what this is saying is that we have our tuning parameter here, or our intercept value, and then and we're going to set it to what we would expect it to be for A, because you notice we have f equals b here and f equals c. So without those here, our baseline is going to be what we would expect, assuming that our factor is set at level A. And then we adjust, if it were to be B instead of A, we're going to adjust by this beta B. And if it were to be C instead of A or B, we're going to adjust by beta C. Okay. So basically what this looks at is what I just said there. So if f equals A, what we're going to have, our expected value of y, when f equals A is going to be beta naught, because basically these are going to cancel out and be zeros up here. If f equals B, then it's going to be that beta naught value plus beta B. And then if it's C, it's going to be beta naught plus beta C. But in other words, we can think of this. And again, this scenario we're portraying right now is just using one factor as the predictor, no other values. Okay, we're not looking at any other predictor variables. We're just looking at one predictor variable that's a factor. So when that's the case, our expected value, our beta naught is going to be the average value of A, the average value of Y for group A. Our beta B is going to be the average value of Y for group B minus the average value of Y for group A. And then beta C is going to be the average value of average value of Y for group C minus the average value of Y for group A. So it's easy to see how this interpretation can be extremely useful when you are looking to compare treatments to a baseline. Most computer programs default to this method. Okay, again, from a coding standpoint and from an interpretation standpoint, in terms of what you're used to, this baseline approach is what we're going to focus on. And I'm going to show you that down below here in just a bit when we look at an example, but I want to show you the other methods that we can compare and contrast them to when we get down to the code. So the other way to fit this model is simple. We use a direct model, which says the expected value of Y given F is A to A. The indicator of F equals A. And then A to B, indicator of F equals B. A to C, indicator of F equals C. Okay, so really what this is doing, this becomes, the interpretation is very simple. It basically means that our expected value of Y is going to be the mean of that entire group's Y values. Okay. All right. So that makes sense from that standpoint. But the other thing I will say is this approach gets to be a little bit more challenging to interpret also when we add additional predictor variables. So we just want to be very, very cautious of that. And that's, again, why we're going to teach and focus more on the baseline approach. Okay, so let's go ahead. I'm going to move this over and we're going to look at, go back into RStudio and we're going to run some examples here. Okay, so we're going to look at the baseline and we're going to go back to the UN data that we've used previously. So I'll go ahead and run this. And in this case, I'm going to go ahead and attach the data. You could do it either way. We're going to go ahead and look at life expectancy real quick. Before we do that, though, let's just do a quick refresher. Let's first go over and look in our help do help, UN 11, and let's just refresh our memories on what our variables are. Okay, so we're going to look at life expectancy, female life expectancy in years, and then that group variable we haven't looked at in a while. So remember, it's a factor with 3 different levels. So OECD for countries that are members of OECD, which is the Organization for Economic Cooperation and Development. And then Africa is the second level. And then other for all other countries. Okay. And another way to check our levels. So, you know, we don't always get this handy dandy help file, especially when using external data sets. So another way to check our levels is we can do a function here, levels. Here, I'll even add it into the RMD file too, so that you all will have this to reference. But we will do levels of group, and we'll run that. And it tells us down here in our console now that we have 3 different levels and what those values are. Okay. So we're going to model just looking at the one predictor variable, the one factor predictor variable, its impact on life expectancy of females. So we'll create our mod. And now we're going to look at the summary of that. Okay. We're going to do some examples where we look at the interpretation of this. But right now, the really important thing to start looking at is I go straight to my p-value and say, okay, good. It's showing that they're, you know, at 0.05 level of significance, this factor is significant. There is a significant relationship between the group and the life expectancy of females based on my p-value. Okay. Now, if you look over here, you're going to actually see these are not actual variable names in our data set. It's the variable name followed by the option. And you'll see we have group other and we have group Africa, but we're missing one. Okay. We had 3 levels, but we're missing one, and it's that OECD. Okay. So what it's telling us is that, and again, going back to what we saw in our HTML file when we were looking at the math behind this, okay, our beta naught or our intercept value is our expected value of the first factor level that we have. And in this case, that's OECD, because that's the one we're not seeing show up here in the list. So it's telling us that we would expect the life expectancy of females for OECD countries to be 82.4 years. Then if it goes, you know, if the group changes to other instead of female, or I'm sorry, instead of OECD, then we're going to see a decrease on average of 7.12 years. If the group changes though from OECD to Africa, we're going to see a decrease of 22.674 years on average. Okay, so that's how we're going to interpret that. And let me just make it even more obvious as to what this is saying. So we're going to run this t-apply, and we see here that we have OECD, and what this is doing is it is applying, so it's splitting life expectancy by group and taking the mean of that value. Okay, so we have the mean life expectancy for OECD is 82.44. We'll look back up here at our intercept value, 82.44. That was the expected value. 75.32 for others. Well, let's do some quick math here. We have 82.446 minus 7.12. Yep, we match. So the average of other is what we're expecting to happen here. And then for Africa, 59.77226. Okay, again, we can check our math real quick. 82.446 minus 22.674. And again, we have values that match, okay? So this is pretty straightforward when we are just using one predictor variable and it's a factor, okay? Obviously, this gets more complex when we add in additional predictor variables, but you can at least see the mathematical approach behind all of this way. Okay. So let me scroll back up here and just, because again, I told you that I would make sure to kind of type up some notes as we go. And then so I'll just add it right below this code chunk here. Okay, so to interpret this, the model, we would say that on average, life expectancy of females is 82.4 years for OECD. For other countries, we see an average decrease of life expectancy of 7.12 years. And for African countries, we see an average decrease of life expectancy females of 22.67 years. Okay, so that's how we would interpret that. And we could also note our p-values show a significant relationship at 0.01 and 0.05 levels of significance. Okay, and I want to put this in here because I will say, as you all approach your homework assignments, this is an area that can continue to use some improvement from some of you all, is the interpretation of the model. And this should become, you know, you do it over and over and over again, and it's like you're doing it by rote after a certain point in time. Okay. So that's that baseline approach that I talked about. So basically these coefficients are the changes from that average value for the first level of the factor. Okay, this down here, let's scroll down here real quick. This is the coding approach to that second, for the direct coding option that we talked about. That again gets a little bit more complex for interpretation when you are looking at adding additional predictor variables. So we're really not going to do any more of this after this, but I'll run this for you real quick. So mod 2, we have life expectancy of group -1 is how this is going to work. And if we look at the summary of that, it actually gives us the average life expectancy for each of the 3 groups is what that output ends up looking like for us. Okay, so just so you can compare and contrast the difference. Again, if you just have the one predictor variable, one factor predictor variable, you're fine, but otherwise it gets a bit more complex to interpret. Okay. All right, so now we're going to look though, like I mentioned, we often have more than one predictor variable. So let's add a continuous variable to our model. Okay. So we're gonna switch back over. Let me pull this over real quick. All right, scroll down just a bit. Okay, so now we're gonna add our continuous variable in an example, but before we do that real quick, let's just talk about what this does for us, how this changes things for us. So our continuous variable is going to be X. So basically it's taking that original baseline model that we had and adding one more variable to it with beta1 of X, which we're used to seeing anyway, because previously we had beta0 plus beta1 X, so forth and so on. Okay, so what this is telling us now is that pretty much all of our initial scenarios with our factors of our different levels A, B, and C, we're just going to add beta1 times X to that equation to give us our expected value of Y. All right, so let's look back over here. We're going to now look at still our UN example. We're going to look not only at the group that the country is in, but also log PPGDP. So let's take a look at that real quick. All right, so now we have down here, we have our intercept value. So we're saying, you know, baseline, if it's the life expectancy of females is 49.52 years. And keep in mind, we're looking down here, you'll notice again, we only have 2 of the 3 groups listed. And then we have log PPGDP listed as our additional variable. Okay, so it only splits out the factor ones, the factor variables. So we have our intercept value 49.53. That would be our expected number of years if log PPGDP were equal to 0, and if our if the group were OECD. Okay. If you look over here, you will notice that not all of our p-values are super, super small. We have this one, this group of other of 0.193, okay? So it's saying it's a little less significant, but we can't toss it out by itself because it's technically part of the entire, like this is only one of 3 parts of that variable. So keep that in mind. You're going to see this in some other examples. As long as one of your factor levels is significant, we would still probably state that there is, you know, we would definitely be able to state that there's still a relationship. There's still a relationship that variable, that predictor variable has on the response variable. Okay. So just because one is maybe not, you know, the p-value is higher, doesn't mean we're going to toss out that entire variable in our model. All right, but it's saying now, again, holding, just like we did on our interpretation of our models with more than one predictor variable, we state that holding all other predictor variables constant, so holding log PPGDP constant, if we just change the group from OECD to other, we're going to see a decrease of 1.5 years. Or if we change it to Africa, we would see a decrease of 12.2 years. Okay. And then as log PPGDP increases 1 unit, we see, and we expect on average an increase of 3.2 years. All right. So I'm not going to type up the interpretation for that because again, this is following suit with what we've been talking about before with multiple predictors. We're holding all other things constant, and these coefficients have either an increase or a decrease effect on our response variable. All right, before I get into this next section, any questions on this so far? Again, I think, you know, if you guys have been following well with all of the model interpretation we've done to date, being able to add in predictor variable factors is not, categorical predictor variables is not the most complex thing to wrap your brain around. So not trying to rock anybody's world this week. All right. So when I introduced this in some of the notes earlier on, we talked about how sometimes you might have with these categorical variables, you might have multiple lines, linear relationships with different slopes. So you basically end up, or, you know, you have different slopes for each group and how you might approach that. Okay. It sounds complex and it is. So we typically steer clear of it from a model interpretation standpoint. And I'll explain that here in just a bit, but there's still a way that you can do that. So basically different intercepts are useful. They're useful, but you know, if we have 2 completely different lines, it makes things, you know, it's simple mathematically and code wise to add that. We basically add an interaction variable, but it's much more complex for the interpretation part of your model. So an interaction is when 2 variables are multiplied together. Okay, so again, we're going to go down, we're going to look at the same data set that we were just working with. And we'll get to it here in just a minute, but we're going to look at group times log PPGDP. So that creates an interaction variable. And what it does is it's going to basically create several different scenarios for us. It's going to look at just the impact that the group variable has, what log PPGDP has, and then the two variables multiplied by each other. Okay, so I'm going to go ahead and switch back to this screen and we'll start running that. And when you see the output, it'll make a little bit more sense. All right. So scrolling down to my console here, like I just mentioned, it keeps all of our original variables here. So our intercept is just, you know, we're thinking that OECD is our baseline. That's our initial factor. And then the impact of changing the level to either other or Africa, and then log PPGDP's effect as well. But we can't interpret it as straightforward as what we just talked about in the previous example, because now we have this group other times log PPGDP and group Africa times log PPGDP. Okay. This could be a better model for us performance wise. It could have a better, a higher accuracy. So even, let's see, multiple R squared here for this model is 0.7498, and our earlier one was 0.7492. So technically this model explains just a tiny bit more of the variance than the model we just looked at, but it is much, much more difficult to interpret. Like Brad and I would not even attempt to interpret this model. You're not going to be able to go into an executive and explain the impact all of these different variables and interactions have on your response variable. Okay, so really this goes to say, it's a trade-off, and it goes back to what's your goal? What kind of a role are you in? What are you trying to do? If you're really focused on being able to interpret the model, and then you don't want to include these interaction variables. If you're more focused on model performance and you trust AI and machine learning to do, and your organization has leadership that's really backing of that, and they don't necessarily need to understand the details of how it's working, then this could be an effective solution. I will say that's not often the case now, because there's more and more push for more transparency in how these models are built and interpreted. So just be very, very careful of interaction variables. You'll see here in bold letters, we never interpret single variables when we have higher order variables in a model. Okay, we just, they no longer become, they're basically obsolete at that point. So if we have those higher order variables, those interaction variables, we don't try to interpret. We have to remove those interactions before we look at creating some sort of interpretation of the model. Okay, so just wanted you to kind of see what that would look like, but this would result in you having, a model that basically treats every single group differently and all of the subsequent continuous variables pertaining to that group differently. Okay. All right. So the last thing we're going to do is another example here of a predictor with factors. So like I mentioned, we have that house selling prices FL CSV that we had previously used in this course. It is posted again right there with this RMD file, so that if you need to re-download it, you can do so pretty easily. So I'm going to go ahead and read in this file from where I have it saved locally. Again, you could, if you don't, know the path to it, you can basically replace all this with file.choose, and then parentheses around an empty space there, and it'll open up a new box for you to be able to go select it if that's easier for you. Okay, so real quick, let's refresh our memory of our variables here. So we have a house, we have 100 houses. Okay, so that house is just the number. So it's the record number or the observation number. Taxes, bedrooms, number baths, quadrant, northwest, because we'll see here in a minute, but the majority of our homes are in the northwest quadrant. So that northwest is either a 0 or 1. It's a binary variable. Price, size, and lot. Okay, so I was right. I was hoping that it would be in this example. So I mentioned that looking at this summary, look right here, quadrant. And let me show you this too, just so we can see it even better. And this is why looking at the head of your data is really helpful too. So FL price, go ahead and run that. And I see quadrant, NW, SW. So it looks like, you know, at least in the first few observations, there's really only two levels to that. In the northwest, I see 0 and 1. But when I go back up here to my summary, it's viewing quadrant as a character value. That's the data type it's seeing it as. And then northwest is seeing as a numeric value instead of like a binary factor. Okay, so if you want to force any of your variables to being factors, which I have to do it all the time, you can just do it this way. We're basically going to overwrite the quadrant variable as dot factor. So we're going to convert it. So let's do that for quadrant. And let's also do it while we're at it. Not that we're going to use it in our model, but just for practice, we'll also do it for that northwest or NW variable. So FL price, W. Okay. And so I'm going to run this as well. And now if I rerun summary of FL price, again, FL price is just what I named it in my environment. You could name it whatever you want. But now if I go over here, I can see quadrant. I have northeast 17 observations, northwest 75, southeast 1, southwest 7. And then northwest, I have 25 zeros and 75 ones. Okay, so that tells me a little bit more than just, you know, before where it recognized quadrant as a character data type and northwest as a numeric data type. And now we can do a little bit more with our modeling. All right, so next we're going to go ahead and build our model. So I have FL mod. I want to look at, let's first just look at the impact that quadrant has on price. Okay, so I'll do FL mod, price given quadrant, and I have my data set in there. And then let's look at that summary. All right, so first thing I'm going to go look at is my p-values. So looking at this, you know, like I said, even if one of the factor levels has, you know, a low p-value, you're probably okay. But I'll be completely honest, I'm looking at this and I'm like, well, I mean, there doesn't seem to be a significant relationship with southeast or southwest, but maybe northwest, but it's still pretty close to 0.05. Like I'd like for it to be a little bit further from 0.05. I think I can probably get, you know, a better model if I look at some additional variables. Okay. Now I could interpret this absolutely, but I'm questioning its level of accuracy and validity just based off of this. So this is where I'm going to say, well, also I look back at my summary and frankly, southeast and southwest, there were so few observations that it's going to be hard for those to have much of an impact, no matter how many predictor variables we add in there. And that's okay. But what I do want to look at is maybe adding one more predictor variable in there that I think might have an impact on price. Okay, obviously a lot of those variables would, but let's just look at the relationship now of size plus quadrant and talk about interpreting that. So we'll rerun our model. It overwrites it because I didn't rename it. We'll look at that summary. Okay, all right, we'll look at that. Now it's showing our northwest quadrant actually, you know, much lower p-value. Southeast and southwest are lower, still not as low, but again, I didn't expect them to get that low given how few observations we have in those quadrants. But this is helpful, okay? So what this is telling me that assuming the size of the house to be 0, which is not feasible, and the quadrant to be northeast, because that's the one factor level that's not visible here, that we would expect the price to be negative $19,987. Well, yeah, no, that's not realistic. So this intercept value is our tuning parameter. Okay, then from here we can say, and I'll go ahead and start typing this. Oops. So from here, we're going to say that, you know, with size and quadrant, so we do see a significant relationship with our p-value of size being less than 0.05 and 0.01 levels of significance. At least one of our factor levels is also significant at those levels. So there is a relationship. Okay. So on average, as size increases 1 square foot, we expect to see an increase of $77.31 on average in the sales price. Holding all other variables constant. In the sales price for homes in the northeast quadrant. Okay, because again, that's our baseline. We're assuming that it's in the northeast quadrant. Now, if the home is located in the northwest quadrant, instead, we expect to see an increase of $36,322.92. In our, or on average, in our sales price. And okay, and then we continued on. So if the home is located in the southeast quadrant, we expect to see a decrease of $39,459.61 on average in our sales price. I mean, you can literally start copying and pasting the sentences if you want. And it does not like these dollar signs because it looks at it as formatting, so it's fine. Take that out. All right, and so like I said, sometimes it's easier, especially with multiple factor levels, to just copy and paste. So we'll go ahead and here, if the home is located in the last one would be southwest quadrant, we expect to see an increase of 26,313.14 on average. These changes in quadrant or changes in price based on quadrant. Assume that we hold all other variables constant. Okay, so that's how we would interpret that. We could also comment on the multiple R squared and say that this model accounts for 65.28% of variance. And that's how we would do our interpretation of that. All right, so that is the example of this. And this is good because this is about where I wanted to wrap up. So Wednesday, we're going to look at when we have categorical variables as our response variable instead of predictor variable. Okay, it's a little bit more complex. We're just going to scratch the surface of that because you'll get into it in a lot more depth if you're taking BUDA 451. But I do want to make sure that we cover it at least from a high level on Wednesday, and we'll make sure to cover an example. So any questions on this before I let everybody go? Okay. Well, thank you all. Like I said, I will update the file on eCampus with what I just worked on. So I'll save those changes and upload that so that you all have that to reference. All right, have a great one, and I'll see you on Wednesday.